Thank you very much. I appreciate the opportunity. Copeland appreciates the opportunity for NASRC to allow us to talk about this study. It's a study that Copeland commissioned with an engineering firm, Future Green Now, specifically on low side year-round energy saving strategies. So this is the first time we've actually presented a full presentation on this topic. And, if you look at that schematic there, that system schematic, I've got all the cases, the medium temp, low temp cases, all circled in blue. I'm not talking about the machine rack really, or the gas cooler and its interaction. We want to focus on the cases and how we can possibly get some annualized or year-round energy savings. So, but before I get into that specific study, I thought it would be useful to let you know that, we have worked on other studies, and it's really interesting when you spend a lot of time working on a study with a specific consulting engineering firm, you learn a lot, right? And one of the studies is on CO2 climate study, we call it, and one on the far left here. And it's all about high ambient mitigation strategies that we've done for 166 cities. And we've grouped those cities into climate zones to provide the information. When you get this PDF of this presentation, you can take a picture of that QR code. It'll bring you right to that white paper. We also did a study with on total cost of ownership, the one in the middle here, TCO, with Cushing Terrell and Hussman. We looked at 8 different supermarket system architectures in various climate zones and compared the total cost of ownership. So that's out there. We recently also finished a heat reclaim study on space heating with Henderson Engineers. Now that's just kind of launched about less than a year ago. So again, a lot of information there on embedded carbon and energy saving differences when you compare CO2 heat reclaim to HFC. And of course, the topic we're going to be talking about today is CO2 ultra low or zero superheat strategies. And we called it the ultra low superheat study to keep it short, but it's all about low side strategies to save energy. And again, that QR code is active. So let's get into it. I mean, the study evaluates the impact of evaporator TDs, evaporator superheats, optimizing saturated suction temperatures, all that to improve annualized system efficiencies. And some of the key observations that we made in this study was that, and some of these observations you may say, well, they've been around forever, but I'm highlighting them to show the importance that it's still valid, whether it's an HFC system or CO2 system. So we're talking about lowering superheat on booster systems. It's really an emergent suction side strategy for optimizing year round. So we've heard about that. And you may be familiar with jobs that have gone in where you're running 0-degree superheat. And I'll talk about what those strategies look like in a few minutes. Other observations is reducing the superheat and increasing your suction pressure will lower, obviously, your compression ratios. And that improves system efficiency because the compressors are not working as hard. And the third thing we've got down here is the benefits of increasing saturated suction temperature by reducing the temperature difference. The evaporators you select for the lowest temperature load, if you can reduce the TD on those evaporators, you effectively increase suction. And I'm going to talk a lot about that as well and its implications. And all this came about, we're having internal discussions in Copeland about studies that are coming out of Europe and technologies that are coming out of Europe. And, we're thinking that despite reports of the effectiveness of some of these ultra low or zero superheat strategies out of Europe, there was really no data available to validate its efficiency potential on US DOE certified display cases and unit coolers. So that's when Copeland approached Future Green Now and said, hey, we'd like to work collaboratively here to understand when we look at all of the US DOE certified cases, and some of those TDs can be pretty low, what impact do these strategies that have started in Europe have on our cases here in North America? That's why we started this study. So that's one sliver of what I'm going to talk about today. The four main stages of this strategy that we've wanted to look at was, number one, evaluate the impact of evaporator coil temperature difference on the lowest temperature load. And that was number one. Number two, evaluate the energy saving potential of splitting your suction, having two suction groups. That's not new. The industry's been splitting suctions for a long time. And with CO2, we came back to one centralized rack, one centralized medium temp suction, and low temp. I know that some of them are starting to split, but there may not be actual numbers out there, energy saving equivalents to splitting it. So what we've done in this study is kind of showed you what the impact of doing that could be. The third one is evaluate low to no superheat strategies. What are those strategies? What do they look like? What kind of benefits can you get out of them? And then the fourth one is compare them all. Let's take all the low side strategies, the dual suction, and how do they fare out against high TD evaporators, average TD evaporators, and low TD evaporators from an energy efficiency perspective. So that's what the study set out to do. Now I'm just going to kind of go through the results with you. So display case unit coolers that are DOE certified. So in this study, we looked at 214 display cases by 5 different manufacturers, laid out all their specifications on a spreadsheet, and made sure they were DOE AHRI 1200 certified. We made sure we captured the operating conditions, the rating points, the superheats. You could see here that we've got medium temp superheats. On average, they were somewhere between 6 to 8. Low temp superheat varied from 3 to 6. Captured that. Understanding the coiled TDs. Some TDs out of those 214 cases were as high as 10, as low as 4, and average around 6. So we built that into our model to understand the impact of those different TDs on the lowest temperature loads. And then we looked at 51 unit coolers that we thought was kind of interesting. They had DOE, they had to be AWEF certified. Every single one of those by various manufacturers showed a superheat rating point of 6.5 degrees. And what was interesting to us is all of them were only available with a 10-degree TD. It kind of limits you there, but it is what it is, and that's what we worked with, and that's what we built into the modeling. So what were our system assumptions? Let's take a look at the system on the left. Now, this is a basic booster system, and you'll notice throughout the presentation, the colors mean something. I've standardized on the colors that red is going to be your high pressure discharge and your gas cooler out. You have a high pressure valve on every system, a bypass valve on every system, our flash tank. The orange is our liquid line. Green will always be medium temp suction, and blue will always be low temp suction every time you look at a chart. So it kind of aligns you directly in what's going on. On our modeling tool, we used meat deli temperature ranges, and I'll show you what they are. Cold room ranges, you can see the unit cooler for the cold room, and beverage and produce. Those are our 3 main categories on medium temp. And our main categories in this study was frozen food, frozen freezer, walk-in box freezer, and ice cream in a standard booster configuration. So dry gas cooler, not adiabatic. We're focusing on low side strategies, 95-degree gas cooler out, 400,000 BTU medium temp loads at plus 18 saturated suction was our baseline number that we worked with. Low temperature was 100,000 BTUs. So 1/4 of the medium temp was low temp at minus 25 SST. We limited the condensing to 59-degree minimum, saturated condensing. Flash tank was set to 38 or 537 pounds. And the condenser TD, while operating in subcritical mode, was around 14 degrees. Well, it wasn't around. We used 14 degrees, and in transcritical mode, we used 6. Now, you may say 14 seems a little high, but we've done this before in that maybe if a gas cooler, we're assuming that they're starting to lose a bit of efficiency due to dirt over time, instead of making it 10 and maybe not giving the real life scenario. So that's why we use 14 there. We assume suction line losses in the medium temp of 2-degree equivalents, which is about 13 pounds of pressure drop, and 2-degree equivalent low temp is around 7.5 pounds. So you'll keep seeing that show up on diagrams because it's important when we figure out what our saturated suction at the compressor is. Future Green now used equations, energy equation solver software, modeling software. We used NRail TMY3 and weather data. And we just focused on 3 cities for this study. So we had to develop a baseline system. And this is our baseline system that we compared all technologies against. Once again, when you take a look at the schematic, we've got medium temp compressors, 400,000 medium temp at a plus 18 SST, discharging, and our baseline system had heat exchangers, internal heat exchangers, to assure that we have the right medium temp superheat. Now, I'm not showing all the valves in the system. I'm not showing oil separators, oil reservoirs. I just keep it as simple as possible. High pressure valve, bypass valve, flash tank. Come out of the flash tank, you have another internal heat exchanger to assure that my low temp compressor superheat is maintained at a minimum 36 degrees. And the reason that we added these internal heat exchangers is that so we could get as close to the optimal superheat that those coils were designed to operate at. Because a slide earlier, I said the superheat ranged from anywhere from 3 to 8 degrees, depending on the coil, depending on the manufacturer. So for our optimal baseline system, we use 5-degree superheat, knowing full well that the industry in North America today uses 10 degrees for all of their evaporators, medium and low temp. And we're going to use 10 degrees on comparative systems. But our baseline uses 5 because it's more efficient, lower superheat. So that's what we've done. Now, our evaporators, you can see here, are meat delis at 30 degrees air, discharge air. We're using the highest TD coils at 10-degree TD. That means that my saturated suction for my meat deli is at plus 20. I have a 5-degree superheat, so I've got 5-degree return gas temperature. My cold room's at 34-degree air, 10-degree TD. I have 24 saturated suction, 5 degrees of superheat. And then my beverage cooler, out of all the coils that we looked at, the 214 coils from the beverage cooler, the highest TD we could find was 8, so that's what we used. So 38 minus 8-degree TD gives me a 30-degree saturated suction with 5-degree superheat. Now you'll notice that there's a star here next to the meat deli because that's my lowest SST on my lineup. And I've got 2-degree equivalent suction line losses. That means if I've got 20 SST, I lose 2 degree. That's why I'm sitting at a plus 18 saturated suction for that medium temp suction group. If we look at my low temp, minus 6 frozen food, 10-degree TD, I've got minus 16. I've got minus 14 SST for my freezer. And my ice cream is expected to be the lowest SST. That's why I have the star, minus 23. plus you lose 2-degree equivalent line losses, I'm going to be at minus 25. That's how I got my minus 18, score medium temp 18, and minus 25 low temp. Baseline system. So let's evaluate the different TDs, evaporator TDs, on the lowest temperature load, and what does that look like? So as I mentioned, when we went through this study, we established display cabinets, standard average temperatures you would get for those cabinets are somewhere around 30 degrees. So that's what we stuck with. Cold rooms, we set them all at 34, and our beverage produce at 38 for medium temp. And as I mentioned, 2-degree line losses. In this example, the highest TD was 10-degree coils on the first two and only 8 on beverage. So my lowest SST, as I've already discussed, is 18, my common suction. And my low temp, we use -6, -4, and -13 for ice cream. Driving to a saturated suction with the highest coil TDs of -25. Now, what does that look like when your coils get a little more efficient? So instead of using the highest coil TD, I'm using the lowest coil TD here. Instead of the display cabinets being 10, it's 4. So I can go from plus 18 now all the way up to plus 24 SST. My unit cooler is still 10-degree TD, and it's at plus 22. And my display cabinet's now gone from 28 all the way up to 32. So now my lowest SST is a plus 22, not plus 18. On my low temp, it becomes plus 19 because now I've got 4-degree TD on that case instead of 10, and that has a huge play. And then we've got the average coil TDs and what that would look like if you'd be interested. But when you take a look at just going from high coil TD to the lowest available, there's a big jump there. And the jump occurs in your suction pressure. That's where your efficiency gain is. At plus 18 common suction, I've got 394 pounds. If I can go up to plus 22 by changing the evaporator design on that lowest temperature load and get up to 420, that means I'm 26 PSI higher suction, which means now my compression ratios just reduce. The total heat of rejection is reduced. There's less stress on the condenser, and the compressor uses less energy because the compression ratios have reduced. The same thing happens on the low temp, going from 181 at minus 25 to 204. That's a 23-pound increase. So again, the same strategies would make sense. So when we look at this particular system using highest TD evaporators, and I've got plus 18 SST on the medium temp and minus 25 on the low temp. And I've showed all my equivalent losses and everything else. This system is all operating at 10-degree superheat. And you can see here by 20-degree SST, 30-degree return gas temperature, I've got 10-degree superheat. That's what we use because standard systems out there today in North America are running with 10-degree superheat. So some of the key points that we've discovered, of course, is evaporator TD on the lowest temperature load sets the compressor SST. And we see that here, and we see that on the ice cream cooler here. TD determines the saturated suction required to maintain a specified air temperature. Now, these evaporators, if it's designed for 10-degree TD, of course, it's going to be able to give you the actual discharge air that you require with that 10-degree TD. If it has a 4-degree TD, it has a different design in order to also provide you that same temperature of discharge air, but doing it with less temperature drop across the coil. And a lower TD results in higher SST, which we've talked about in the previous slide. Those are key points that are very important to compare. Now, the initial outcome of the study that we looked at looked at baseline architecture with the internal heat exchangers that I talked about using 5-degree superheat, right? These are DOE HRI operating points that we follow. And we wanted to compare that to a system using average coiled TD. And the average coiled TD were around 6. And you can see here on the medium temp deli, we use 6 TD. Cold rooms, we had no choice because the only thing available was 10. Our beverage cooler was 6. So now in the medium temp, I have 2 that are at the lowest SST. 30-degree air with 6-degree TD gives me 24-degree SST. The same as the cold room, 34 air minus 10 TD gives me 24. So we're at 22, 24 minus 2 degrees. So now we're at 22 degrees saturated suction there. But my low temp increased slightly because of the ice cream. Now, instead of having a 10-degree TD, I've got a 7-degree TD. And that brought me up to a minus 20 SST instead of a minus 23, which increased my common suction. So what does that mean when you look at this and you look at the average savings? By being able to take this ice cream and go from a 10-degree TD to a 7 and reduce my meat deli from a 10 to a 6, that gives us 6% annualized savings. That's year-round savings. That's not just during a certain few hours a year. This is all year because that evaporator with that low TD is in there for the life. So 6.8% savings versus the baseline. Now, what if you had the lowest? What if you had 4 degrees? 4-degree TD here doesn't make any difference on medium temp because you're limited to the cold room 10-degree TD in this example. On my low temp, however, you do gain a bit more. We're at minus 19, and that gives you an extra 1.1% additional savings going to the lowest available TD on that ice cream. And you can see from the numbers below, 18 degrees going here from 18 to plus 22. That's a 26-pound increase in suction pressure. So there's a definite advantage there. And going from a minus 25 over here, which is 181 pounds, to minus 19, that's a 23-pound increase. So again, now even your low temp compressors, total heat of rejection is less. The power used is less because the compression ratios have just reduced. And that all ties into the fact that now it puts less load on these medium temp compressors to do the work. So you get an extra 1.1% savings annualized. So when you summarize it, you say, okay, my baseline system that I talked about, 5-degree superheat, internal heat exchangers to assure that we have 20-degree minimum superheat medium temp, to assure we have minimum 36-degree superheat at my low temp, and still get effective use out of my evaporators as efficient as possible using 5-degree superheat. But these had 10-degree TD evaporators, or the highest TD evaporators. We compare that against an average TD, 6.8% increase, and lowest TD, you get an extra 1.1 or 7.9 annualized. So that's one phase of the study we wanted to look at, straight TD. The next part of the study we wanted to look at was an energy saving potential of splitting the suction. And like I said earlier, it's not new to refrigeration to split suction. We've been doing it forever and a day. But you may not have had the numbers when it comes to CO2 to be able to justify it if it costs more, because there are some costs associated with it. So let's take a look at what we've done as part of this study. We started with a system that had 400,000 medium temp at a plus 18 and 100,000 BTU low temp at minus 25. So what we decided to say, okay, we're going to split that, of course, into two medium temp suction groups, two low temp suction groups. Now, our medium temp one will be 240,000 BTUs at plus 18. And our low temp one will be 70% of the low temp load will be at minus 18. And then our second suction group, medium temp, will be 160,000 at plus 28. Significant increase at plus 28. That's 10 degrees higher in medium temp. And then low temp will be minus 25. So when you look at it on a schematic, we've split the suction. So these two compressors are for medium temp one, which is handling 240,000 BTUs. The lowest suction tied to these compressors is my meat deli, because we've got the highest TD available in this example. So I'm running a 20 SST and minus 2 degree equivalent suction losses, brings us to plus 18. Okay, plus we have our cold room. So those two, plus we've got the bypass valve, which dumps into, which provides a bit of desuperheating, but also provides a lot of load, which does no refrigeration. And then on the low temp side, our minus 18, which is 70% of the low temp load, is also discharging into the M1. So a lot of things going on this chart. The higher suction, which is our beverage cooler, is running at a 30 SST with 2 degree line losses. So we're at a 28 SST. That's a big jump. We go from 394 pounds here to 462 pounds at a plus 28. So that's a significant increase in suction pressure. So again, that particular compressor's compression ratio just reduced, its total heat of rejection just reduced, and the stress on that gas cooler goes down. And the efficiency of this specific compressor goes up relative to the others, or it's the amount of energy that it's using goes down relative to the others. And our minus 25 discharges into here. So that's what we've done there. And when you look at the pressures, I've kind of overlaid them on there. So if you look at the PDF, I've listed the delta in increased suction pressures on medium temp and the increased suction pressure on low temp, and to kind of show and justify where these energy saving values are coming from. So the next logical question is, well, how does that strategy with that breakdown compare to a single suction baseline system that I've talked about a couple times already, using the highest evaporator TDs? There's a 7.2% increase savings. This is year-round savings. All you've done is split your suctions and made sure your low temp loads were going to the right areas. And you can have a 7.2% annualized savings using the highest TD evaporators. Now, how does that same system compare with highest TD evaporators versus lowest TD evaporator? Take the same exact system I just showed you. I've got mostly 10 degree TDs on the left here. And then I take that exact same architecture, and the evaporators that once were the lowest SST, now I've got a 4 degree TD instead of a 10 degree TD. It's no longer the lowest SST coil. That gets shifted down to my cold room because of the TD on that one. So now I've got a plus 22 here. Now my ice cream that used to be at a 10 degree TD and minus 23 is now with a 4 degree TD at minus 7, which drives a significantly lower saturated suction, minus 19, instead of minus 25. And I've got minus 16 on this particular 70% of my load versus minus 18. Again, all the suctions have gone up. However, this particular M2 suction went up even higher to a plus 32. So even higher suction on this particular case. And when you compare highest, exact same dual suction, comparing dual suction to dual suction, the only thing we've changed here are the evaporator on the lowest temperature loads. 6.9% year-round energy savings. So one thing to look out for, though, it's all fine and dandy to do all this and increase your suction pressures, but you have to be mindful of certain things. Now, what I've listed here is M2 capacity, M1 capacity, 240,000 BTU, medium temp. That's why it's in green. Well, the L1 is LT1 is dumping into MT1. But what's interesting here that I wanted to point out is the SST of the MT2. This is the higher of the two, the higher medium temp common suction. Depending on the TD of that beverage cooler, my SST, the saturated suction on the highest TD can be 28 degrees. It could be 30, possibly up to 32 degrees based on coil TD. Now here's the pressure that translates to it. Now it looks great because that compression ratio keeps going down as the evaporator efficiency gets higher and the suction gets higher. However, we need to keep in mind we have to be able to evaluate the oil management strategy to make sure that adequate oil pressure now across the oil level regulator will be enough to satisfy the compressor. And what I mean for that, I know I apologize for the little tiny picture in the bottom, but let me just take a second to review what I'm talking about. We've got a compressor, and I'm not showing it on the main chart, but our medium temp compressor discharging into an oil separator. Of course, it has a coalescent filter and impinges the oil. The oil falls, of course, to the bottom. Discharge gas continues off to the gas cooler. When that oil now is at the bottom of that oil reservoir, it gets transferred by pressure to, oil separator to an oil reservoir. Now, typically that oil reservoir is equalized to the flash tank. So if the flash tank is at 520 or 530, that means the reservoir pressure is going to be around 520 to 530 pounds. Now remember, if on M2 over here, I've got anywhere from 28 all the way to 32 degrees, that means my suction is quite a bit higher. That means the differential across that oil regulator from 520 to 491 is only 29 pounds. Is that right? 29 pounds, which might not be enough differential to satisfy the compressor feed in 120 seconds. So you may have to look at that and modify your oil strategy to make sure that that M2 compressor gets the proper oil feed. And if you're already designing, you're already working on systems with parallel compression, you have to take that in consideration already. You need to take that mindset from parallel compression and apply it to the M2 oil circuit to make sure that you have adequate pressure differential across your OMC oil control to satisfy the needs of that compressor. Okay, that's what I wanted to point out when your M2 pressures get higher than normal, if you will. So the other thing I want to talk about is evaluate ultra low or no superheat strategies with DOE certified display case and unit coolers. And this is how it all started. I remember I said at the beginning, we're sitting around saying, yeah, it's great, all this data that's coming from Europe, but we don't have any US data that we can compare against. And what does it look like? So that's why we started this strategy and kind of extrapolated to other areas. So when we look at the evaporator efficiency, typically you could have a pinch point at the air entering point, or you could have a pinch point at the air leaving or desired temperature. And pinch point is that minimum temperature between air and refrigerant temperature. And that can happen at either end of the spectrum, if you will, depending on what kind of strategy you're using. I use the example here. My air entering temperature is going to be high. We all know that. That's why it has to go through the evaporator in order to reduce the temperature to its desired point. Well, as the refrigerant enters that evaporator as a saturated liquid and vapor, right? The percentage will change based on the saturated temperature of that coil. But we'll assume here there's no pressure drop in this evaporator, so that my line here is nice and flat. So as the refrigerant travels through this evaporator, of course, it's removing sensible heat, as many BTUs per pound that it can handle, right? And it's been designed for sensible heat removal all the way down to this point where you got that liquid vapor interface occurs, where that last drop of liquid boils off. That last drop of liquid boils off right here. And now we've got sensible heat gain, which just does not remove a lot of BTUs in your coil, but the refrigerant continues to increase in temperature or superheat to protect the compressor. So the pinch point here, the minimum air temperature in this scenario with a 10-degree superheat coil would be at the air entering point. And this coil would be designed, let's say, for example's sake, I've got a 10-degree TD, and those coils are designed to remove, an example, 100 BTUs per degree of temperature difference. You've got 10 of them. So that coil is designed for 1,000 BTUs to heat removal plus X amount of superheat leaving the coil. And I showed you earlier that the DOE certified coils will range from 3 to 8, depending if it's low temp, medium temp. So now when you look at a 0-degree superheat curve or 0-degree superheat, what really is going on here is now my evaporator is able to remove sensible heat throughout the entire surface. It doesn't stop here. It has a couple more passes to remove sensible heat, so very efficient heat removal. So even if that coil now is rated at 10-degree, 100 BTUs per degree TD, but you've got more surface area to remove more heat, then it might be removing more heat than it needs to. So if you can elevate the suction pressure and reduce the TD on that evaporator, you'll get the same amount of heat removal. So now my pinch point would be here instead of at the other end. So we're looking at that kind of strategy when we look at liquid ejectors, for example. This is one of the strategies to have either ultra low or no superheat. So my system looks the same. I've got my compressors, I've got my discharge gas cooler. Now this device, instead of being a high pressure valve, it does act like a high pressure valve, but it's the liquid ejector. You can see there's 3 connections to it. Discharge or gas cooler out, flow to my flash tank, and I've got flow coming from this device. This device is a suction accumulator or a low pressure receiver. Now, if you're going to, and we have a bypass valve as well, we have an internal heat exchanger. You've got your medium temp. So liquid ejectors, when activated to have 0 superheat, they need a case control that has a capability of switching from normal superheat to 0 superheat. So if you do have low 0 superheat, you're using the entire surface of that evaporator remove heat. You're able to float that suction up a bit, but the resultant is you can have liquid coming back. So that liquid cannot make its way to the compressors. So it drops into this accumulator and it starts to fill. And as that liquid's in the bottom, that ejector has the capability of drawing it out and mixing it with the high pressure and returning it to the flash tank. So this is really what we're looking at. The high pressure motive force comes into the ejector through the throat area, picks up speed, supersonic speed, which creates a vacuum effect, and it draws liquid out of that suction accumulator, mixes it with the gas cooler out, and returns it to the flash tank, and is being managed and controlled effectively, like a high pressure valve would. But the benefit is it's not allowing liquid to get to the compressor, it's siphoning it out. So that is really the effect of liquid ejector. Now there's some benefits to that, of course. You can operate evaporators with very low to no superheat, increasing your medium temp saturated suction, which is the goal. Help to overcome some efficiencies with high evaporator TDs. That's very important. And you're going to see that on the next slide. It really helps to overcome inefficiencies that I showed you of high TD evaporators on that lowest temperature load. And it also provides you year-round energy benefits. Now, like with everything, there's some challenges. Only used on medium temp evaporators. Adds system complexity because you got ejectors, you got suction accumulators, you've got interaction here, you've got proper means. You also need to manage the oil return from suction accumulator to the compressors, because like with any system, oil travels, CO2 travels with POE, and it will get deposited in the bottom of the accumulator. So you have to have means to make sure that you're picking up that oil and it doesn't continuously just get trapped in there. So that you need to be aware of that. And also you need additional components, piping, costs, and your main system control has to have the ability to integrate with the case control to make sure that you can flip back and forth between normal superheat control and or zero to ultra low superheat management. So that's the integration. So what are the energy savings with ejectors? Based on our study, operating 8,760 hours a year. So we had to make assumptions, of course, that this thing ran all the time and it ran to peak efficiency all the time. So if you have a 10-degree TD evaporator, you'll get almost 11% energy savings. Now, this is the least efficient of evaporators, of course, 10-degree TD, but you can make up for that with liquid ejectors. If you have a more efficient evaporator on that lowest temperature load, then you'll gain about 4.4. If you have the most efficient, it's 3.2. So the descending value depending on how efficient your evaporators are from a TD perspective. The other strategy we looked at looks kind of familiar, but we still have a low pressure receiver / accumulator. We are able to run our evaporators to zero superheat, but this particular strategy is called liquid to low temp. There's some OEMs that have different names for it that are tied to their own company, but from the strategy and what it does, what we have here is medium temp evaporators, as I mentioned. You have to have the capability to communicate with a case control, once again, to be able to move from standard superheat to ultra low superheat. And if you have liquid coming back, that liquid get deposited in that suction accumulator, low pressure reservoir. And the OEM would measure the liquid level within this receiver accumulator and energize a solenoid valve and de-energize the main liquid line solenoid valve feeding the low temperature cases, so that now I'm feeding 20-degree, roughly, liquid to my low temp cases instead of 38-degree liquid or 36-degree liquid. Now, another thing to note, the suction pressure in medium temp, if we're saying using round numbers, 400 pounds. My flash tank is normally around 520 pounds. So even though I have 20-degree liquid coming out, I have 400 pounds of pressure instead of 520 pounds. So my pressure drop across the valve is reduced, but it is made up by the fact that I've got subcooled liquid. And of course, when you're designing, you got to make sure that the capacity of the valve at 520 and 36 degrees is equivalent to 400-pound inlet at 20-degree liquid. So those are things to look at. When we calculated our energy efficiency, we assumed that these low temperature cases were all being fed by 20-degree liquid 10% of the time. So 870 hours a year, they would all get that, and that was part of our modeling assumption. Benefits when it comes to that: can operate evaporators with very low to no superheat, resulting in, again, increase in medium temp suction. Help to overcome some inefficiencies in high TD evaporators, same as the liquid ejector we talked about. Ensures energy benefit year-round. Provides higher enthalpy liquid feed to low temp evaporators when accumulator is full. So that's different. That's what I talked about here. Some of the challenges: adds complexity, requires additional components, piping, controls, and integration with case control. Proper means of oil return from suction accumulator. These are three things that were common with liquid ejectors. The low pressure receiver sizing and switching liquid flow from the main flash tank to the suction accumulator needs to be well understood and properly operating in order to benefit for what we're talking about. So now you apply liquid to low temp to a 10-degree TD evaporator on the lowest temperature load, you get 11.5% saving, a little bit more than the last one. You get 5.1 on a 7-degree TD evaporator. Again, this is not just medium temp, because there's some value there for that subcooled 20-degree liquid. So that's why these numbers are a little bit higher. And 4 degree is 3.9. So now let's take a look at dual suction with evaporators optimized superheat. So one thing we also wanted to look at, let's take a look at the dual suction now that we can drop the superheat on my medium temp 1, medium temp 2 down to 5 degrees, and also drop the superheat on these at 5 degrees. And when we look at that and we provide some benefits, it says here, provides greater energy savings compared to liquid ejectors and liquid to low temp strategies when using 7 or 4 degree evaporators. There is an advantage there that I'll show you in a graph in a few minutes. Simplicity: maintain system existing structure without the need of additional technologies. You get efficiency gains, improve energy efficiency for both medium temp and low temp suction group. It's a year-round efficiency gain, as the others were. Delivers consistent energy with energy efficiency through the year. Yep. So some of the challenges with dual suction will be additional costs. It requires added investment for suction piping, compressors, drives, because you're splitting them up. Design dependencies. So unit coolers and display case specifications must align with the design of the evaporators. So making sure that you optimize as much as possible. Must provide adequate oil flow to OMC oil controls, oil level regulator on the highest SST suction group. That medium temp 2, you need to be aware of it and solve that. Know what you're going to do if you're going to raise that higher. So with the energy efficiency value of dual suction with 10-degree TD evaporators, it's not as high as the others on the 10-degree evaporator, but it is higher on lower TD evaporators. So 7, you get 6.1. And even 4, you get around 6.3, which is almost double with the other strategies when you're using the lowest TD on those suction groups. Again, using 5-degree superheat, we have internal heat exchangers. You can see low temp internal heat exchangers, and for the medium temp 1 as well. So let's compare these strategies. This is kind of near the end here. My baseline, of course, is my standard baseline design, 5-degree superheat. My average TD I'm comparing against. Liquid ejectors, you saw here. This is basically a rinse and repeat of those individual slides I showed you earlier. Liquid ejector, you can see 10.9. Liquid to low temp for 10-degree TD, 11.5. Dual suction dropped to 7.2 on a 10-degree TD. However, dual suction outperforms the other two for 7-degree TD and 10-degree TD. Okay? Now, if you were to stack them, we'll take a look at that in a second too. This is what I've just showed you. The annualized or year-round energy savings with highest degree evaporator on the lowest SST load, 10.9, 10.5, 7.2. But if you have the lowest coil TD on the lowest SST and you compare liquid ejectors to liquid to low temp to dual suction, if they have the lowest TD coil and the lowest temperature, you automatically get a 7.9% bump. And what's my additional adder on these technologies? Dual suction will give you 6.3. Liquid to low temp, 3.9, additional 3.9, and liquid ejector, 3.2. So that's what the study showed. So when we break it down and said, you know, a summary and key takeaways, we can achieve savings by using lowest TD coils available on the lowest temperature load. We can realize additional savings, though, by adding an internal heat exchanger and allow the system to operate based on the design coil superheat. Instead of keeping it at 10, you're down at 5, 4, even 3 in some cases for low temp. Number 2, you can gain additional energy savings by adding ultra-low superheat strategies. Yes, we can do that. We've shown that. The amount will vary based on the percentage of year-round operation at the low or no superheat point. If it's operating 8,700 hours a year, you'll and it working properly, you'll get the numbers that I've shown. If you're not operating those hours, of course, that will vary. The savings will vary. Dual suction has equal or better energy saving potential as the ultra-low superheat strategies. The amount will vary based on the load split, the evaporator design, and the coil TD. So those are our findings. If you actually take a photo of this, it'll take you straight to the superheat study, and you'll also have it in the handout. And the last thing I wanted to say, if you were not aware, if you're using Copeland Mobile, there's a new feature there called Scout. It's an AI feature that can really help you out, because I was playing around with it earlier, and one of the things I asked Scout, I just said, hey, what's the recommended suction superheat for a ZO compressor? Boom, it started doing a search, and immediately it came up and it said, the recommended suction superheat for a ZO scroll compressor is to maintain, to always be above 36 degrees Fahrenheit or 20 degree Kelvin to avoid oil dilution in the compressor. And then it went on to say other stuff, and it gave us the application engineering button, bulletin. So if you're not familiar with it, give it a shot. There's a lot of information in there. And that concludes my presentation.